So I want to talk a little bit about isochrone maps and intermodality. But before I really start, I want to know who of you guys have heard about here technologies? Lift your hand. Ah, that's more than I expected. Yeah. So we are the guys behind the scenes. We are a B2B company. So I will have a short introduction who we are. I will not go through everything what we do. And then I will jump into isochrones. It was already mentioned by Leah. I will be doing a deep dive. Then we talk about intermodality, for instance, park and ride. And then the favorite topic in this uh, symposium is schematics and real maps. So, short introduction. By the way, this I took in Montreal during the last symposium. That's, I think, Jarry, Métro Station Jarry. A very beautiful transit station in Montreal. So, we at here, we do also maps, surprise. So, we are in map mapping over 25 years already. So, if you don't know here, we were formerly known as Navtec, then we were known as Nokia, and then we were known as Ovi, and then now we are here. And I know all the here jokes, so don't even start. So we do also maps, and next to maps, what we also have, what people don't realize, we have also APIs. Here, this developerc.com, so feel free to just go there. Most of the APIs are from the start free, up to 250,000 requests or whatever you're using. And we have all kinds of APIs you can start using, and everything I will show today is using all the public APIs we're offering. So basically, anybody of you could have done this presentation, obviously. So apart from all these 100 APIs we have in our company, from geocoding, search, traffic, transit, we have transit, routing, intermodal, and traffic. These are falling under routing and navigation, but we have also a million other APIs for rendering of map tiles, transit layers, and stuff like that. So I will encourage you, just try it out. We have also SDKs for Android and iOS, and mostly, so it's basically free to use in the beginning. We also have an app. We are not really competing with anybody in the space. We know there's Google Maps, there are Move-It, transit apps, but we have an app basically just as customer facing, which also works completely offline if you want, worldwide, except Japan and Korea, I'm sorry. But otherwise, we also have transit layers, and we also have indoor maps, like you can see here. You would click enter, and then you would zoom in, and you would see the layers and what stores, what shops are in what region. So that's already to here. We are part of Here Transit, now called also Here Urban Mobility. Since years, our heart is also beating for transit. We do all kinds of stuff. We have relatively a lot of freedom to try out new things as well. And this is also something we will present today, some new things. For the next symposium, we also have already something in the pipe. So basically what we have is this offering, and we have a transit cloud offering. Basically, we are sourcing all the transit data as many of other aggregators do. We have a routing engine with a lot of services. So we don't provide just A to B. We provide basically all the service you need as a transit rider. So station search, nearby station, coverage, information about the lines, service alerts, Isoline routing, vehicle positions, very interesting. Sometimes we have real-time data, and sometimes we predict the vehicle position. And it's always nice, maybe later when I have time, I can show you on the map how all the buses and transit vehicles are moving on the map. We also have departure boards, and we have also the dynamic transit routing and park and ride. So as I said, this is more a platform offering. And underneath, we have all the maps, parking data, and PT data. So our company has really a lot of location data. We have all the parking lots in the world, or we believe we have. We have the maps and the public transport data. So what we do with this? This is our coverage. It's a bit old. It's from last December, but still holds up. As you can see, we have these blind spots. We are working on that. I hope we can work with Naver on this. That would be great. Other than that, I think we were well covered, and we are also happy that more and more movement is going towards open data. Um, Especially in Europe, it was very hard to get data, especially in France, but that changed. So it's really great. And we also know how concerned public transport authorities are when you're using data and you use your own routing engine, because there's always like this notion that the authorities would like to have they planned their network in a certain way and would like that the routing is reflecting that in a certain way. So we try to respect that as much as possible. So in order to do all these transit data on transit data, we heard yesterday Leo, he has this GTFS home movement, which we really support, because we get data from all kinds of agencies. Most are okay, but there are many bad ones. And there are even some people that give us CVS files, Excel sheets, Markdown I've seen. So it's very interesting how transit data exists. When we are lucky, there's GTFS, HAFAS, or MENS data. These are usually bigger companies that have more cleaned up data. What we do is basically we also try to normalize, convert, and enrich them. Sometimes the graph is not inside the transit data, then we try to recreate the graph. As we have satellite maps, we try to map the transit or the rail network onto the stations and then recreate from the satellite maps the transit rail network for the real graph. We also combine data sets, because if you, for instance, New York City has 22 plus transit authorities, they're not talking to each other really. But if you're a user, you want to move from A to B, you don't care so much except for the fares. So we also combine these data sets and publish them basically in a catalog. So 100% automated for most cities. Some cities are somehow changing their intern or their output filter. I don't know what it is, but the data is fluctuating. Sometimes there are parentheses, uppercase or lowercase. There's something we try to capture. So 15% manual work required for complex cities. So we have a whole team doing night and day just transit data engineering. So that's why we'd love to see a standardized GTFS. And we update around 20 cities up daily. And we have also a lot of real-time cities where we update every 30 seconds for this the real-time feeds. So that's about here transit. And now I go into isochrones. This is one of my favorite topics because it's very different from schematic maps, but I try to marry it with schematic maps. So I was last year in Beijing, and while I was in Beijing, I got from the hotel this one schematic from the hotel transit map, and I was thinking, I can zoom in this area, just this. So I was living here at Guomao, and I wanted to make a picture of a new structure, which is called the Galaxy Soho, which is just here. So I thought, great, just 2 stations. So I was thinking, well, transit in Beijing, if you know, they have metal detectors, you stand in line, a lot of security, you really wait until you can enter the transit station. You cannot just run into this transit station. It's much more complicated. And if you don't have the yuan and cash, you even can't get a ticket. So it's very limited. So I thought I walk this part. So it was a little bit hot. I agree. It was the hot summer. Korea had also the hot summer. China had it too. It was at that time 38 degrees and 70% humidity levels. But I thought, well, I look young at least. And I used to travel in the neighborhood from Zag. This is a Rub al Khali desert from the doorsteps. And I'm used to walk in extreme situations. So I packed my bag and started walking 2 stations, walking. After half an hour, I didn't even saw one transit station. It was just great. I was like, maybe I'm lost. Maybe I've missed it. So I pulled out my maps and I saw I'm not even halfway. So these 2 stations actually were very far away. So, and I realized, okay, schematic maps is nice, but it doesn't give you a notion of how far it is actually. So I ended up to look like this. It wasn't rain. That was really it's my own stuff. Yeah. So I took a cab in the end. So looking back into schematic maps. So schematic maps are very nice, but they are not spatial um, because they are distorted. And this is a beautiful map, by the way. So they are distorted, right? So they are not spatial. They're not telling you how far everything is. Nor are they temporal. They also don't tell you how long does it take for you to reach one of these stations. They're actually just a connection graph, right? So if you want a spatial map, you go to the real map. If you want a connection map, you go there. But what do you do if you want a temporal graph? So what can I reach in 20 minutes? And this is where the isochrones come in. So actually, if you think of many problems you have, you often think in isochrones, but you don't see them. It's like, what can I reach in 20 minutes? It's like more a personal, opportunistic map of from where you are at the moment and what you can reach. And it's also not so easy. We just saw in the presentation before here, you see already nice isolines here for pedestrians. Here's a 5-minute ring, here's a 10-minute ring. We do the same approximation. It's not really valid when there's a river in between. I would be surprised you can reach that with 10 minutes, but it's pretty good enough. We do the same approximation. So basically with the isochrone, you see already how far you can reach things. This is how it looks for cars in Paris. So the inner color is I think 10-minute ring, and then 20 minutes, 30 minutes, 50 minutes out, and so on and so forth. So this similar isochrone you saw already in a presentation before. Surprisingly for transit, it looks very different. Actually, it doesn't look anything like this. Some people of you know already how it looks. It looks like bubbles. Because you travel in stations, and in between, you're not getting out. So basically, this is an isochrone in, where am I? London? London, yes. Yeah, there's an isochrone in London. And basically these, the center of these bubbles are basically your transit stations. And then you approximate basically how far you can reach with pedestrian. We can also generate real isochrones. I did that in the beginning. I asked them for the isochrone for pedestrian for every station you get out. Then I got a call from our colleagues from the pedestrian servers, and they said, you're taking down our service. Because if you play around, you send thousands of requests to do so. So I went back to bubbles. It's good enough. But I think they're beautiful. So they are almost a piece of art. So, and every city, if you take the center or like a specific spot, has a different signature. And I saw it in a different company. They have even posters for every city, the isochrones from the city center, which is and just this without the map. So I think it's also a form of art. Very beautiful. And you can actually play around a lot. So this is, for instance, for Paris at a certain station. And basically, with the opportunistic map, you can also turn it around. You can do a lot with that. We know we have customers. They say, okay, they sell apartments. And what you can do is like you pin your workplace and say, I don't want to live further away than 20 minutes from my workplace with public transport. Then you can basically search in all these areas. Unfortunately, here you don't see the map, so what you can do is invert it, and then you have basically the isochrone map, the stuff you see you can really reach. And that you can do with our API, so you can print your personal map from basically your home place. So then there's a specialty about these isochrone maps. I want to show you something more interactive. So here we have Paris, and we can check from Gare de Lyon. This is where we are. This is how it looks like. And basically, you see already here's a legend. You can see this is the furthest out is 60 minutes. And basically, you can drag this and move it to any place you want. And it's immediately calculating the isochrone for this place. You can also zoom in to see it better. So, and what's also interesting actually with isochrone is we have seen just in the presentation before, public transport is about frequencies. This is just in this moment, but it changes by the minute. So let me move it back here. I can put up here the time, and then you can see how it changes actually by the minute. So it's basically breathing when you make an animation. And that's also very beautiful. If you animate this, how your reachability changes by the minute if you miss a train or miss a bus, right? While in the city center, it's not so dramatic if you move it out to a bit further out. Close. Then you see already, this is more dramatic because your connection is less frequent usually. So we can play it here. Let's see how this changes. So if you have a friend and the friend is living on the other side, right, and you want to see, well, where's the middle? Where do we meet in the middle? On a schematic map, you really don't see it. You can basically place another isochrone and then see where you meet. Oh, they're not overlapping really. Let's say it's here, and then basically where you can meet. So you can play a lot. You can do a lot with isochrones. If you have a spouse there, kindergarten there, an affair there, so you can really search where is my optimal home, basically, to reach all these places. While we're doing this exploration, what you can also do, you can add a car in this tool, and then you see also if you live in the outskirts, basically you could do something like park and ride, right? This is the optimal route is basically the overlap where you see then a transfer station where they overlap. There you transfer into a PT network, and this would be the optimal route to their destination, right, where this little bus is hanging. So basically you could do park and ride. It's not so easy. My colleague will talk about that in a second. But playing around with that is very great. And you would think also much more in isolines. Every time we have a brainstorming sessions and we try to come up with new patterns, we figured out all the ideas we have is just a homomorphism comes back to, it's just an isoline implementation of something. So it's a really powerful tool. So coming back to the presentation, you saw breathing. So let's take again Paris. Now I want to do really something like park and ride. Park and ride is becoming also is more and more in fashion as the Dieselgate was there. We get more and more environmental zones in different cities. How easy is it actually to solve park and ride? So we are not designers, we are more like technical people. These are all the transit stops in France, in Paris, sorry, a great area. And these are the parking spots, the bigger ones that can be used in Paris. So if I overlap them, you see already there's quite complex problem. If you want to calculate a route, you don't want to go through all this permutation that kills any server at the moment. So you need basically a more sophisticated system to do so. So Ilya spoke already a little bit about the complexity of multimodality. Basically, this is how people move. I try to make a state diagram. This is what computer scientists do, a state diagram. How do I get from A to B with what mode, right? Just to see this is my origin. Then I have a walk, then here car share, or I go to public transport. Then I skip or I take a flight when it's overseas. And then I take again a taxi or a car or a bike. And then I arrive at the destination. So this state graph you can play through. This is basically all the different modes, how you can go from A to B. And we tried to solve this in full first. We had an example, I think it was from Berlin to Chicago. We came up with 1,300 different options how to get from A to B. It's not something we can present to the user. Here you have 1,300 options. Choose your best. And it's also difficult because you have, especially for car sharing and bike sharing, you have different subscriptions and sometimes different fares. And but what you see here in the center is always public transport. So we consider public transport is always the backbone of every city. And if you talk about multimodality, it's mostly public transport involved. I've rarely seen somebody driving with a car and jump onto a bike share. I would love to see that. So that is not even modeled here. So it's mostly you try to get to public transport or you try to solve the last mile from public transport. So, and this is exactly what we've focused on. And who knows which transit station is this? Exactly. Very good. I hand over to Andreas. Yeah.
Thank you, Jens. My name is Andreas. I'm for the first time in the transit mapping symposium. I'm very glad to be here and to talk, to give you an example of what we do and how we do stuff. So let's zoom in into park and ride. Oh, wrong button, sorry. So I'm just a little bit confused, right? So we edited slides just recently, so they're not in sync. Okay. So first of all, what is a park and ride route? So it's integrated experience which could be presented to the user in this way. So you start with the car. So the car part has all these maneuvers, instructions, turn right, left, and so on for 20 minutes. Then you have 5 minutes to park, and you are led to a parking lot. Then you have 10 minutes of transfer, walking to the transit station, and you continue your journey with by public transit, right? At the end, you have additional 5 minutes of walk to reach your destination, right? So we have here seamless mixture of modality within one route. It starts with car and goes to transit. It incorporates dynamic information for car part and for the transit part. So meaning information about traffic, traffic incidents, traffic jams for car, transit delays or disruptions for transit, and then of course dynamic information about parking. So like availability, live availability, and predicted availability. So why did we come up with this idea? Why doing park and ride? So to whose benefit? And we see like it has advantages from multiple different points of view. So you have the user, or like usually a commuter from a rural area, who can in this way avoid stressful driving situation. So avoid standing in the traffic jam, avoid expensive and stressful parking experience in the city center. So you have government and cities, as Ilya mentioned in the previous presentation, and I'm very thankful to him for spending so much passion to convince that public transit is actually the backbone of the future urban transportation, due to growing worldwide population, due to growing urbanization rate. What we also see in the European Union is the legislation for the clean air. So you have the directive which dictates limits of nitrogen oxides in the cities, and majority of European cities actually violate them. So including those from Germany, France, UK, Spain, Italy, Poland, and so on. So cities are start banning diesel cars, because diesel cars are seen as the root cause, or like 70% of all nitrogen oxides emissions are assumed are caused by diesel car engines. And finally, at here we like create new advanced services. We like combine existing assets and create something new out of it. So how do we do park and ride? So this is a little bit of illustration, right? So if you think about it from the routing algorithms point perspective, then you see the challenge that car routing works a little bit differently than transit routing. For car routing, you would use Dijkstra algorithm. For transit routing, you have other algorithms like Raptor, CSA, or trip-based. Like I'm not aware of any scientific work which is describing how to combine both routing graphs in one and how to have an algorithm which can find you the best route in the combined graph. But maybe that's not needed, right? So maybe we just combine, maybe we just use car algorithms for car part and transit algorithms for transit part, and use parkings as intersection points. So basically on this picture, the blue part would be the car route from origin to all possible parkings within the intersection area, and the green would be transit route from all parkings to the destination. So very like naive approach. So why it was not so easy? Of course, it's the high complexity, so which you can try to circumvent, and we did that. So we filter parkings, we remove irrelevant parkings, those which are far away from transit stations, because they will not be used anyway. We made some optimizations for the intersection areas, so we don't use the bounding box or the square, but we try to do it in a more smart way. So another restriction was, as Jens mentioned before, it is sometimes very hard to get the transit data in Germany and France, which are our key markets. So the solution had to work in those markets, despite us not having the full routing graph. So the transit agencies in Germany and France, they tend to entertain they own transit solutions, and they are very protective about their data. What we get is usually their access to the transit API, which gives us the route from A to B, but nothing more. And finally, once we created a park and ride route, we need to determine, is it a good one or is it a bad one? We don't have clear criteria for those. So as I said, we reduce the complexity a little bit by using heuristics, but how did we solve the problem of not having the transit graph? So we used estimations, right? So essentially we created estimated isoline around every parking lot. So we sliced the area around it in 8 segments for every geographical direction: north, south, west, north, south, southwest, and so on. We used the prop data, so some route requests, and analyzed the duration to distance correlation. Okay, so then we built those sophisticated curves and used regression analysis to approximate the distance duration correlation. And then we fit a curve and store the coefficient for every direction. So in that way, we had for every stop a quick lookup for how long it would take to get from there to the final destination. Next challenge was to decide, do we create a good park and ride route, or is it rubbish, right? So for car route, you have quite clear criteria. It is either fastest or shortest. For PT, you also have quite clear criteria. So it's fastest by arrival time or least transfers, or it could be also the cheapest one. For park and ride, it was not that clear. We tried to use machine learning. We created prop data, and we let real users, rate their park and ride routes. But we quickly ran into the issue that we had a lot of variety in the rating. So the same park and ride route would get very different rating. And we quickly understood that this is because of different user preferences. So we took a step back, performed the user research, and try to put the results into the test framework, right? So we had a lot of useful learnings, like if I'm doing the park and ride route, then I don't want to have any transfers on the transit part, so I can take the detour with my car. But if I'm on the transit, then I want to have the direct connection. Rapid transport types are preferred, so nobody wants to stand in the traffic jam on a bus. So not every city has dedicated bus lanes. Users want to have full transparency of the external costs like parking and PT, because usually those are car drivers, they are not familiar with transit. So we identified those different scenarios, and I'm gonna present you those. So first scenario is the pre-trip planning. So you try to so like when you are at home and about to drive to work, or you sit at the car, you build the route, you look at the different options, how long it will take, to which parking lot it will lead you, and so on, and then you decide which route to take. So another situation is on the go. So essentially you are driving with your car and suddenly an accident happens on the road, and it's kind of eject or emergency button, um, which brings you outside of the traffic jam to a parking lot and lets you continue by public transit. So those are three different strategies which we implemented. First one is park early, so where commuters from rural areas really use their car only to get to the closest, let's say, regional train station and continue the journey by transit. Another case is park late, where you try to get with your car as far as possible inside of the city and then transfer to transit before environmental zone, before the congestion zone, or before the built up areas, or drive and then park on the go, right? So if something unplanned, unexpected happens while you are driving. So the solution which we developed works worldwide, and I'm gonna demonstrate it to you in a minute. We learned that users accept and appreciate such a service. However, they are very picky about the quality of the data. They expect very precise and dynamic data. We are currently performing a pilot project with the Deutsche Bahn in Stuttgart. So, as you might know, Stuttgart has banned diesel cars from the whole city area. So it's 80 euro penalty if you enter with a diesel car. You can download the DB Park and Ride app. It's for free. And we have in-dash integration, so built-in navigation system in the next Audi generation. Okay. Yeah. So now let's see it working live. So maybe I would start with that one. So this is our reference client, where you can actually play around with the API a little bit and get the visual experience of how well it works. So I'm creating a route from somewhere outside. This is the car route in blue color, okay? So now I'm trying to create a park and ride route. Create a new tab, select park and ride. Use the same pins. So it's calculating. I'm closing the car route because it's a mess. So like what you see now, right? There were 3 routes calculated and returned. This is the duration, 1 hour 14 minutes. It starts with the car, translates to subway. So the blue line stands for the car. The violet line is the subway, line 6 in Berlin. So this is the transfer point. So this where you have the parking. So you can switch between the routes and see that they are almost the same, right? So just the transfer point is different. You can try to show the same in Paris. We have very slow internet connection, so the map tiles are not loading. Okay, so while it is loading, I'm going to show you something else. So it's kind of racing simulation between a normal car route and park and ride route. So performed at different times in different cities. Let's take London at 9 a.m. So you start at your location with the car. The lower route is park and ride route. You transfer to the public transit. And then you go, right? So and you see how it goes, right? So you have the white line, then you have the gray line. You had the transfer there. So you arrive at the destination, and the car is still on the way. So this demo is done using real data. Can do the same in New York. Again, you start with the car, but go a little bit different paths because the park and ride route leads you to a subway. You transfer to subway, and then you rapidly continue your journey to. So while car is parking, you are already there. Good. Thanks a lot. I'm sorry. Just one moment. No, still loading.
So just one more slide, and then we are done. Going back to the presentations over here. So now we have seen, there was also the question, right? Now we have seen park and ride, but while you have for transit schematic maps, how do you visualize such a thing in a summary then with park and ride? And there's the question also we asked ourselves, and we don't have a solution, but we had an idea already years ago. Juk visited our headquarters and worked with our map labs, and they came up actually with a quite clever idea, which I like and try to get revived in our company. It's what when you marry schematic and real maps. So transit schematics are an abstraction of reality, right? But how do you show the street network based on transport in schematic ways? This is a super question. I also have colleagues here. They're probably looking into the same thing at the moment. So maybe they are solving it for us. So there was this idea that I let the demo speak for it, that when you zoom out, so this is now the real, when you zoom out, it's slightly changing into a schematic map. So you have this morph. So basically that you're not losing connection between your schematic and the reality, and you can seamlessly move in and out, right? So that might be a version. Then they even played along with the vehicle position on the schematic and in real life, so you can do a lot. So they did a whole mapping between reality and schematic with a complex morph algorithm. That's it. Thank you very much.
Thank you. Question? Yes, over there.
I'm glad you can show it, because it used to be secret.
Yes, but the IPR is saved.
Yeah, I also like how so many slides of this presentation say that this is for internal use. Thank you very much for this presentation. This is really cool. I think there's maybe I didn't quite get 100%. What the final user of what you do is, because I think there are many applications, because this can not only be user, final user oriented, like the person who is traveling around, but what you're doing also is the component that is, I think, a little bit missing from transfer planning field at the moment, because everybody seems to be super obsessed with modeling, or the dynamic modeling simulations of traffic flows and many other stuff, and using softwares like PTV or whatever, and not so much trying to understand how transportation works spatially. And I think the special component is much more interesting because, as you pointed out, this is eventually what we all care about. We ask questions that isochrones are answering to. And one of the things that came to my mind, so it's not that much of a question, but more of a comment. I think that to this we can also add the many other analyses can be done on these bases. For instance, the transit reliability. I was showing in my presentation the reliability diagram as a dotted diagram taken for a particular connection, but it could be really interesting to see the isochrones overlapped one with the other, like one isochrone for the planned service, for the scheduled service, and another isochrone that shows the real performance based on statistics, on how it works, and then overlapping the two, prepare a heat map that would show as green areas where the difference is minimal, and the red areas where the difference is exceedingly great. And this will be, I think, really cool. And as for the point that you made with your very last slide, with the transformation of the maps between the real the geographical map and schematic map, this kind of works as a concept, but I know that in many cases, in many schematic maps, there are inevitable consequences of the need of fitting the schematic map into the real format of where you're putting it into. And for instance, Moscow Metro map has a couple of major geographical inconsistencies in it. So what is your? I think that's where I can ask a question. So what's your take on it? How do you think is gonna deal with the geographic inconsistencies? Will it be understood by users, or will the graphics designers have to do geographically consistent schematic maps?
That's a good question. So I think we are trying this out, right? And the user will decide if it's crap or good or bad. What I think it still works with the morph, because the morph doesn't care about these geographic distortions. What you would see probably is that one landmark is moving slightly across of something which it shouldn't, but you still, as you do it slowly, you don't lose touch of basically how everything is connected. And I think that was this importance, right? If you switch too fast, you lose orientation. It's really just that your eye can follow where everything is. And I think it's okay to have distortions and irregularities.
The idea was to keep the story so that you're not lost in the translation from one form of map to the other. So that's the animation. And it's basic triangulation. So of course the schematic map is hugely distorted. But as it moves slowly, you see the transformation from one to the other. And we didn't meet any problem of that kind. Even though, those are my maps for the prototype, so I know the deformations I made inside them, which are quite huge, just like in Moscow.
Again, this also takes away the anxiety that you might face from using several maps and having to, go from one area to the next. And just a question, but in general, being able to tell the distances and be able to really geographically set your location and then be able to see the schematic part of it as well. I mean, it's fantastic. I really, really like it.
Hi. So great presentation and really cool stuff. Glad to see you guys are working on this. So one of the questions regarding routing and park and ride. So one of the hidden costs that isn't, I think, typically surfaced in parking is circling and trying to find a parking spot. And like when you consider that, especially as a weight, against transit, or other options to transit, something like that, I think it makes the other options more attractive. So I was just curious how you guys took that into account. Do you assume kind of a fixed cost for circling for parking, or I mean, there's all kinds of crazy stuff you could do from real-time data or historical use data at different times of the day. Just curious how you guys handled that.
Yeah, that's a very good question. So indeed, um, if you compare park and ride against pure car, there are many cities where park and ride always loses because pure car, if you don't consider traffic, if you don't consider traffic jams and parking, it's always the fastest. But that's not the reality. So indeed, there has been studies also from IBM. They made a study about the average parking time in city centers. So we take this data in. We do our own studies as well. And also, there was one more thing. So we also use predictive parking availability, right? So it's a real bummer if you do park and ride. We suggest you route, you come to the parking, and it's either closed or full. So then it becomes real painful because you have to go away from the transit station we try to route you. So we also work together with several parking providers and try to get their occupancy patterns. Right, it's not fail-safe, but it's relatively safe, or sometimes even with real-time data. The problem is real-time data. You do the planning like half an hour before you arrive, can change, but most of the time it works. And the same is also with traffic. So we have a traffic product, and we use also predictive traffic from traffic patterns from the last month, also depending on time of the day, season, if there's events, football games, and stuff like that. So all that we have in our databases. And if you do drive live, then we have also real-time traffic. So once you're in a traffic jam, you're not getting out. There's an utopic idea that, well, I just park my car and then go to transit. Mostly there's no transit nearby. So what we try to do is like get you ahead of the time, informed, and say, look, there's a traffic jam ahead of you, and then here park your car. And that's why Audi is also going to integrate this into their cars. And it's very interesting that they came to us and said, we want park and ride from you, an automotive company. Imagine they want you to, in the end, ride, because for them it's more about the experience. They don't want you to sit in the car and then scream, and I don't use the car at all anymore. So they want you to have a good experience. And they said, park and ride is a totally cool option for us. Yeah.
Okay, thanks. And kind of a follow-up question. So do you surface that same parking cost in like drive only versus transit? Because again, that would kind of, that would make transit more attractive if you include the kind of the circling and parking costs.
So we made the experience, for example, and this is especially true for US American cities, that parking outside is much more cheaper than parking in the downtown, right? And every car route ends with the parking, and which is usually not considered and not displayed towards the user, right? So.
Thank you.
So what for northern countries like Canada, sometimes we have snowstorms. And so, this winter we've had a lot of 30, 40 centimeter snowstorms, and they say tomorrow you should not drive and you should take public transit. Would I be able to input that somehow in the app and say tomorrow circumstances are going to be such that not only is everything going to be slower because of a lot of snow, but there's probably going to be more people on the public transit? Is there a way for me to say put in snow mode and ask for a prediction?
I think unfortunately no, not when you're the first one. It will come later once the delay information is generated. Then you would have a better notion of how long it will take you. But we also can't predict basically if how many people use then transit and how full it is. It would be great to have such a pattern. We tried actually to find a pattern between weather and what mode of transport people are riding and if they're riding. So with snow and rain and stuff. But we always try first machine learning. We always throw machine learning at anything because you get good funding for that. But in the end, the data was too noisy. We couldn't find any correlation.
But in that specific case, since it's the city saying you should not do that, you could think of having, instead of only having relationship with public transit agency saying, here is my real-time position for my vehicle, you could have relationship with the city saying, like, tonight, stay home.
Anyone else? No? All right. Well, thank you very much.